Today we'll start with the PN junction. A PN junction is a single crystal of germanium or silicon doped in such a manner that one portion of it acts as a p-type and other portion acts as a n-type semiconductor. And this boundary is called the junction, which means it is a region of transition between n-type and p-type semiconductor materials. This PN junction is the key to all the semiconductor device, and it can be used as a rectifying diode, or another use is the transistor. Here, two important processes involved during the formation of PN junction. One is the diffusion and another is the drift. As you know, in the n-type, the majority charge carrier is electrons, and p-type, in case of p-types, it is the holes. Due to the concentration difference, electrons will diffuse from n-type to p-type and holes will diffuse from p-type to n-type. The layer around the junction, which carry immobile ions and depleted of free charge carrier, is your depletion layer. Now the accumulation of positive charge, that is the holes in the n side, and accumulation of, that is the electrons in the p side, is sets up a potential difference across the junction, and this potential difference stops the further diffusion of charges. Hence it is called a potential barrier, and due to this potential barrier, a electric field is set up across the junction, which further stops the diffusion. The circuit symbol of a PN junction is such a way. This is a PN circuit symbol for a PN junction. For further conduction, we have to do the biasing of PN junction. Now there are two types. One is forward biasing and another is reverse biasing. In forward biasing, what we do, if the positive terminal of a battery is connected to the P side and negative terminal to the N type, then the PN junction is said to be the forward bias. Here what happens, the applied voltage, that is, if we consider it capital V, that is, this is the applied voltage, that is VA, is opposes the barrier potential, voltage, that is VB. As a result, what happens, the effective barrier potential decreases, and hence the energy barrier across the junction also decreases. Now the majority charge carrier, that is the holes from P side and electrons from N side begin to flow towards the junction, and as a result, what happens, the diffusion of electrons and holes into the depletion layer decreases its width. So the forward bias is in such a way. Next is the reverse bias. In reverse bias, what happens, if the positive terminal of a battery is connected to the N side, if it is connected to the N side and negative terminal is connected to the P side, then the PN junction is said to be the reverse bias. Here the applied voltage and the barrier potential are in the same direction. So what happens, the barrier potential increases to VA plus B, and hence the energy barrier across the junction also increases. The majority charge carriers move away. The majority charge carriers will move away from the junction, increases the width of the, here the earlier width is up to this and it is increases to this. So increasing the width of the depletion layer, the resistance of the PN junction becomes very large, and then no current flows across the junction due to the majority due to the majority charge carrier. But for minority charge carrier, there will be little conduction. Now we'll see the BI characteristics of a PN junction diode. So in the case of forward bias, if we plot a graph between V and I, as V is in the x-axis and I in the y-axis, we see that initially the current increases very slowly till the voltage attains a certain value, that is called a cut-in voltage or a knee voltage. It is about for germanium it is about 0.2 volt, and for silicon it is 0.7 volt, and after that cut-in voltage the diode current increases rapidly even for a small increase in the diode bias voltage. So here the majority charge carriers feel negligible resistance at the junction. So in the case of the reverse bias characteristics, what we see that when the diode is reverse bias, it produces a very small current, about a very few microamperes, which almost remains constant with bias. This current, small current, is called the reverse saturation current, and it is due to the drift of minority carriers. It is due to the minority carriers, as few holes in N region and some for few electrons in P region across the junction. Now, when the reverse voltage across the PN junction reaches a certain value, that is the reverse current suddenly increases to a large value. This voltage at which the breakdown occurs is called your Zener breakdown voltage or peak inverse voltage at the diode. So this is the reverse bias character.